Now let us consider the Church encoding of the tree functor. The Church encodings are equivalent as types, but they have different performance characteristics, and they are more complicated to implement. The tree encoding of the free functor is like this, and in order to implement it, we would have to first implement a trait that hides this inside type parameter. We will have to implement a trait that hides this type parameter and the outside parameter as well. So that's why there's quite a lot of boilerplate involved. So first I define this auxiliary type, and then I encode the free functor using the trick that if I look at the type expression here, then this is the same as the map method of the functor. So I can transform this type expression into this, which is an equivalent type. And this is the same as the map method of the functor. And so a shorter way of implementing a free type class in the Church tree encoding is to impose a type class constraint on G, and to declare this as an argument. So that's why I'm saving a lot of typing if I do that, but it's not necessary. It's equivalent to doing it in the straightforward way. Now, the result is that my free functor looks like this. It has a single method trait parameterized by an arbitrary type constructor, which needs to have a functor constraint. And the type of the method is this. Now, we know that the free functor has a functor type class instance. And in the tree encoding, it was trivial to define it. But in the Church encoding, it is much less trivial because of the complicated type signatures of these functions. So these are functions whose arguments are functions, and type parameters are hidden inside. So here is the definition of a functor instance for this type. I need to define a map function that takes a previous ff of a function a to b, and returns a new ff of b, where f is kept as a type parameter throughout. Now, in order to return a new ff of b, the only thing I can do is to create a new anonymous instance of the trait and override the run method. So now I'm here in the run method. I'm supposed to do this. So let me write a function. So now I have the following data. I have this Church encoded ff of a. I have a function a to b. I have an ffc, which is simply a natural transformation f to g, or if you wish, a generic transformation f to g, since f is not necessarily a functor. So given this data, I need to produce g of b. How do I do that? Well, the only way to produce any kind of g is to call this run method from the previous f of a, which will give me a g of some x, where x is up to this f of a, so it's going to give me g of a out of here. There's no other way I can get any g here. I need to run, therefore, this method, but I'm free to specify the type parameter for this run method. So I specify the g, which is given to me here, as that type parameter, and then I apply that to an FFC, which I have. So that gives me a g of a. Now I need to write this syntax and not just run of FFC, because run has an implicit argument, and it will be confused if I do that. This will not work. So having gotten g of a, I just map it through the function f into a g of b, since g has a functor instance. So I do it like this, just very explicitly. So that's my implementation. Now, in order to use this, I need a helper function that will lift values of f of a into the free functor. So that is like that. I need to implement the run method. So the only way to create a value of the free functor is to do this, to have a new ff with a run method. So then I have an FFC, I can apply this to FA, and I get g of a out of it. Since FFC is directly a transformation from f to g, so that's very easy. And another helper function is to interpret a free functor into a given specific functor g. So that is also very easy, just run the function. The run function itself is already the interpreter. That is the defining characteristic of the church encoding. It is the encoding which is assembled out of pieces of the run function. So the value of a church encoded type itself is already its own interpreter. Now, performance tests give me some reasonable results. However, some paper claims that church encodings are always slower. It's not necessarily always the case. You need to benchmark your code if you want to be sure. Now, the problem with this code is that there's a stack overflow because this run method is actually not stack safe. Again, as before I already said, stack safety in the church encoding is up to the implementation of the run method. If the run method calls functions too many times, then I'm not going to be able to make it stack safe in the other parts of my implementation. And can't really be made stack safe. The reason being that I have to do, so the map function needs to do this. I have to apply to this FFC and have to run in the map function. So since map function has to run, there's no way to guarantee stack safety. Every time, if I have a million maps, then I would have a million nested calls here. So that's a stack overflow. Now let's consider the church encoding of the reduced encoding of the free functor. Now, reduced encoding is slightly simpler for the free functor, and so let's church encode that. We can church encode anything, any type can be church encoded. The question is, does it bring us any advantage? It turns out it does, because the church encoding of the reduced encoding of the free functor can be made stack safe. And here's how. So first of all, we cannot do the same trick as before with the type classes, we have to encode directly this type expression. So let's encode it directly. So first we encode the existential type. So we make this trait, and it will have a single case class representing this value. And here instead of B, I say Z. So that's the implementation of the existential type expression. Then I implement this function for all A from that to G of A. So that's this trait with apply method parameterized by A. And finally, I encode the type by having another universal quantifier outside, which is parameterized here. So in this way, I have encoded this type expression. So this is the boilerplate in Scala that is required in order to encode this type expression. Now, to define the functor instance, I'm going to be more careful in order to make it stack safe. So I'm going to pull things out of the run method if they don't have to be reevaluated. And so one thing I can pull outside is to reevaluate the run. It can be done once. So it can be done outside of this run. And if I do that, then I actually can achieve stack safety. Another way that I use the before method, which is my own implementation. My IntelliJ is a bit confused right now. But before is my own implementation of a function composition, which is stack safe. So how do I implement this? Well, it's kind of cumbersome because of all this boilerplate and types. I have a very complicated type expression. It is still a functor. The church encoding doesn't change the properties of the type that we're church encoding. It just adds a lot of functions and parameterized types and quantified types, but it doesn't change the properties of the type. It's just a different encoding of the same type. So clearly we should be able to define a functor instance if we are able to define a functor instance before church encoding. But defining that would just be more work. But this is work done only once. So here's what we need to do. We need to define the map method. And the map method needs to return a new ff of fb, so we return that and override the run method in it. The run method takes an ffc, and now we have the situation that we have this data, and we need to produce g of b. Now the only way of getting g of b anywhere is to use this run, to run this, but running this will give us a value of that kind, which will produce us a g of b. So where do we get that value? Well, we need to get that value out of our church encoded free functor that we had before. So now let's remember that the church encoding is equivalent to the type that is being encoded, so you can extract that type out of that encoded value. So since the church encoding of the reduced encoding of the free functor is basically encoding of this, we can retrieve this back from the church encoded type. Now, the only to do this is where it is done. So basically, we get this free f of fa out of CEFFA, which is basically running it with identity. So running with identity is the way to retrieve the underlying type out of a church encoded type. So that's what we do in these two lines. And we put these lines outside of the run because this needs to be done it doesn't depend on these arguments. It needs to be done outside, and then we also achieve stack safety. We economize on the stack doing this outside of the run function. So having gotten this value, we imagine it. Well, we imagine it just because we need to extract the parts, the fz and z2b parts of this free f. Free f is just a case class I defined right here with this map C. So in order to extract those things, I need to do a match. And this is a key part of the implementation. I'm composing the functions inside the map case class. I'm not actually running the map anywhere yet. I'm only going to be running it here. So this together with putting this outside achieves stack safety. If I remove this and replace this with and then, or if I put this inside into the run function, I will have a stack overflow. Everything else in this encoding is very similar to what we had before. The wrapping, the run is trivial. The interpreter is stack safe. It just runs the map, and we guarantee that run is stack safe. So performance test shows us that this is actually significantly slower than especially creating this method and all these things that come with it. Creating nested maps method is significantly slower than other encodings. But as we will see later, church encoding has certain advantages. So if performance is not of great concern, but flexibility of design is of great concern, then church encoding has significant advantages. So this concludes our implementation of the free functor. Let us look at other free type classes and how they're implemented. The next type class is the free contrafunctor. In order to implement it, let us follow the general procedure. First, we write down the methods of the type class. It has only one method, which has this type signature. We realize that it's inductive because this method returns, again, the value of the type that we are constraining. And also we realize that it has an existential type inside because it's parameterized with this b. Therefore, the tree encoding looks like this. It's, again, we are just following the general recipe. A tree encoding is a recursive type that is made out of a disjunction. The first is the wrapping of the generating type constructor f, and the second part of the disjunction is the method functor. Now, in this case, this is what we need to do. This is the recursive instance of the type. Now, reduced encoding, quite similarly to deriving the reduced encoding for the free functor, we derive it for the free contrafunctor. The value of a free contrafunctor type in the tree encoding will always be of the form that either we have an FB or we apply several times map to FB, which will add, here I forgot direct product sign. We add a few terms of this kind with products of functions and existential quantifiers. The difference between this and the free functor is the opposite directions of the function arrows. So this starts with z1, and then we have a function z2 to z1, and so on, zn to zn minus 1, b to zn, and the result is a contrafunctor parameterized by b. However, the properties of contrafunctor are still such that we need to compose these functions associatively, and we can compose them before doing map, or rather contra map, or we can compose them after doing contramap. That's a composition law. Therefore, the reduced encoding can simply compose all these functions and put them inside a single function of this type, and so the equivalent type is just this, with all these other existential types simply dropped since they are not used. So that's how we derive the reduced encoding. We need to figure out what are the possible expressions and how they can be simplified using the laws of the type class to some simpler type expression. Notice that the reduced encoding is non-recursive, just as it is for the free functor. And I'm going to show code. Now, this free contrafunctor might be a little difficult to understand or to see where it is to be used, but it is just a general scheme. I can take any type constructor and wrap it into some stuff to make it into a type class instance of an arbitrary type class. So for instance, I can take a functor, such as this one, the identity functor, and I can wrap it into a free contrafunctor. So then this will become a contrafunctor after wrapping. Then I can create a contrafunctor program by applying contramap a few times to this. Then I can interpret the results into a specific contrafunctor such as this one. And the only thing the interpreter needs is a function from here to here. And this function example would be something like this, where we take a value and return a contrafunctor. And contrafunctors are usually consumers of values. So imagine you're logging something so a logger is a typical consumer of values. I'm just going to simplify this very much and consider this function as a contrafunctor. And then this would be a transformation from identity functor to this contrafunctor, which is prepending a prefix to a log message. And I'm going to show the code in a few minutes. That's how we would use a free contrafunctor if we needed it. Another important property is that if the type constructor f is already a contrafunctor, then this wrapping does not produce a new inequivalent type. The result is equivalent. The free contrafunctor over f is equivalent to f, just like it is the case for the free functor. Let us look at example code. So here's how I encode the free contrafunctor, the tree encoding. I encode the wrapping case like this, and I encode the contramap case using an existentially quantified type. Then I create a helper function to wrap things. It's just putting it into the wrap case class. Then I create a contrafunctor type class instance, which does nothing but wrap into the type class, into the case class. So there's no computation done here other than memory allocations. Finally, I write an interpreter, which is trivial. You just run and do a contramap. And I implement the reduced encoding. Reduced encoding is shorter, it just has a single case class with existential quantified type. A wrapper for the reduced encoding. Now that wrapper is less trivial because we don't have the wrap case anymore. So wrapping a value of f means we have this reduced case when we put this f here and we supply an identity function in this place. The contrafunctor instance is stack safe because we reduce every function. We don't apply map anywhere. We don't run anything. We just collect all these functions and we collect them in a stack safe way using this before method, which is a stack safe alternative to and then. And here is the runner. So we just run by extracting a value of C out of the value of F, and then running a contramap with the single function that is left. So that's the example I just described. We have a logger with a prefix. Now the writer functor is going to be wrapped into stuff to make it into a contrafunctor. So we have a free contrafunctor over the writer functor. So the fact that it is a functor is just I've chosen this to show that I can take anything, including a functor that certainly is not a contrafunctor, and I can wrap it into this construction, free CFR, and the result is a contrafunctor. So that's an interesting property. So the result is a contrafunctor, but if you look at the contrafunctor's type signature, it is, say, this. It's a contrafunctor in B, but it is no longer a functor. So even if the constructor that we used was a functor, it is no longer functor in B. So it's a contrafunctor in B. So we have, if we do this, we take a functor, like the writer functor, we wrap it into the construction, and we lose the functor property of it. Now it is a contrafunctor. Just to make it clear what's going on. And here's some example code where I have some prefix logger, and I wrap my writer functor, which could be computed after some functor computation. Then I wrap it into a contrafunctor, then I do some contramap on it, and the result can be used. I interpret that, I run this thing, and the result is as expected. The next example is a free pointed functor. A pointed functor is a type class that has a single method other than functor. So if we say that this is an arbitrary type constructor, then the pointed functor class has two methods: the point, which is this, or it is just the same type signature as the pure method in monad and applicative. But since this is not going to be a monad or applicative, this method is called point. It just takes A and injects that into PA. And map. So this is familiar. So what's the tree encoding of this? Well, it's just A. So we follow the recipe. We have the wrapping case. We have the first method, which takes A and returns PA. We have a second method, which takes this and returns P. So that's how we encode. So we have a disjunction with three parts. Always going to be like this. One part is going to be the wrapping, and the other parts correspond each to a method. In inductive type classes, they're all going to be like this, tree encoded. To derive the reduced encoding, we need to have a bit more work. We need to do a bit more work. We see what kind of expressions can be found by using this definition. So we take the tree encoding and reason about it. So either we take an A and apply a bunch of maps to it. So we first apply point to some value, we get an A, value of type A, and then we apply some maps to it. So that would be one possibility. Another possibility is that we take some FA, wrap it, and then apply some maps to it. So therefore, we only have two cases. One is like this, so a general value of this type will be either like this or like this. Well, it also could be a single FA or a single A, with none of those. So if we do have those things, we can compose all of them. And just as we did before, so we just have one function. One function is sufficient. Now, consider the second case. We have a value and then a function. We can just apply this function to a value, and we just have a single pure value. So we can encode a single pure value, therefore, and we can encode a function times, a functor wrapped times a single function. And if we just have this, we put identity function in there, as we did before. Therefore, the reduced encoding has only two cases. One is a pure value, and the second is this, the wrapped constructor times a function. And it's not recursive, so that's very nice. Note that this is exactly the same as a free functor over fz. So basically this is what we have. If the type constructor f is already a functor, then this is equivalent to f itself. Therefore, a free pointed functor over a functor is just this. It is a very simple expression. So just adding the type A to a functor makes it into a free pointed. So that becomes a pointed, and it's actually a free pointed. And of course, if it is already a pointed functor, we should not use this construction, because then this would be not the same as the functor itself. So unlike other cases that we just saw, we should not use a free construction if a functor already has the pointed method. Only functor and contrafunctor have the property that applying a free construction doesn't change them. All other type classes will change, usually, when you do free type construction. So for example, free monad over a monad is not the same monad. Free pointed over a pointed is not the same functor. Only functors and contrafunctors, pure contrafunctor type classes do not change under applying the free construction. Let's look at the code. It's very easy. To implement this, we need three case classes that encapsulate these three parts. And to implement this, we only need two case classes. And in implementing the functor is very similar, except now we have a point case. So in the point case, we need to implement the functor by hand. So applying a map to a value of this type, we just need to apply that function to that type. So consider a free filterable. Now the filterable type class was explained in chapter 6. It is not a type class that is widely known, so look at chapter 6 for more details. It has two methods, map and map opt. So these are the methods of inductive kind, or inductive type signature, and they return the type that we are constraining. Now, actually it's sufficient to keep just map opt, because we can restore map from it. So let's not overdo things, and let's just implement one method in the free construction, since we can easily get this out of this. In other words, if we have this function And we can implement this function by substituting a going to 0 plus b here. So the tree encoding has two cases, very similar to the tree encoding of a free functor, except here we have this type signature. If the f-type constructor is already a functor, we can simplify the tree encoding by using the identity, the basic identity of existential types. And then we just obtain this recursive definition. So we get rid of the existential type. And this recursive definition can be visualized as an infinite disjunction like this. So it's fa, f1 plus a, f1 plus 1 plus a, and so on. So clearly, applying filter function to this will give us this, applying filter to this will give us this, and so on. So it's in this way it's implementing the free filterable in the tree encoding. Now, this is not the most economical encoding. Reduced encoding actually is like this. It is non-recursive and very concise. In order to derive it, we do the same procedure as we did before. These are mistakes. This should be existential type quantifier, not universal. I will correct this in the slides. Now, an arbitrary value of this type in the tree encoding would be fa, to which a bunch of mapopt have been applied. So that will give you a product like this. Now, using the laws, remember that these are composed using the Kleisli composition, because these are of type A to option B, so these can be composed since option is a monad. So that composition needs to be done, and it gives us a single function. So that can be done, and if we just have a single FA with no functions, then we encode it like this. So we can still encode it. So that's going to be a reduced encoding. And the most interesting simplification is when f is already itself a functor, then we use the basic identity. And we get f of 1 plus a. So the free filterable over a functor is just this. You can just implement a filter for any functor applied to an option. So for any functor f of option of a is filterable. And that's a free filterable over a functor. And this is a free filterable over an arbitrary type constructor. So we see again that free filterable over f is not the same as f. In a very similar way, we can construct filterable contrafunctors, free filterable contrafunctors. I will not go into details about free filterable contrafunctors because that is completely analogous. Here's the code for the free filterable functor. I'll just show this. This is nothing new in terms of how to implement existential types and recursive types in tree encoding and reduced encoding. Consider now free monad. A monad has two methods, pure and flat map. The map method can be recovered. And in this way, we formulate inductive type class. Now, just a comment. We have seen in previous chapters that type classes can be formulated in different ways. You can, for example, formulate a monad as having methods pure and flat map, or you can do flatten instead of flat map. But flatten does not have the same power as pure and flat map because you cannot restore map from flattened. So you would have to have map here as a third method if you wanted to do a free monad over an arbitrary type constructor that is not itself already a functor. For the filterable, there could be different ways of doing the definition as well. And for the applicative, there's the different ways. But what we need is a set of methods that return the type that we're constraining, the type itself, and not something else. And we need a set of methods that are sufficient. So without assuming that the functor instance is already given, for example. So that's why we choose pure and flat map here. And we can recover map from that. So now the tree encoding is very similar to what we had before, except now it has two places in which we use the same type recursively, free m and free m. So the reduced encoding needs to be derived. Let's derive it. So first of all, let's see what happens when we use the tree encoding and create some values of the free monad type. First, we can take this type constructor and apply a few flat maps to it. Second, we can take this constructor, which is a pure, and apply a few flat maps to it. These are the two possibilities. If we take a pure value and apply a flat map to it, that can be simplified due to the laws of the monad. So if you take something else and apply two flat maps, they also can be simplified to a single flat map with a more complicated function here. Again, this is the associativity law of the monad. So therefore, it is not necessary to have many flat maps here. They can all be collapsed to a single flat map, maybe with a more complicated function inside. So, so then clearly the first element in the product does not have to be a pure. That can also always be replaced. So the first element in the product is going to be FA, or FZ for some A, for some Z. And then we have a single flat map. So we don't need more than one flat map. However, this does not let us encode a pure value A without any flat maps applied to it. So that means we cannot just have one part of the disjunction. We need two. We still need to keep this part of the disjunction that we had here. But we can eliminate FA, and we can eliminate one of the recursive usages, but not the second one. So the reduced encoding is still recursive. It is somewhat shorter, but is still recursive. Now, one comment is that recently the so-called final tagless style of programming has become more known in the Scala community. It has become also known in the Haskell community a few years before. In my terminology, what is called final tagless style is nothing more than the church encoding of a free monad. So you can do church encoding of any type, and you can do free monad without a church encoding. And if you want, you can do church encoding of a free monad, and you have a choice. You can church encode this, or you can church encode this. And that could have different performance implications. However, just keep in mind, I'm not going to talk about final tagless because it's not really something specific or special to monads or to DSLs. It's just a church encoding of a free monad, and You can choose it for certain reasons, or you can not choose it for other reasons. Stack safety is important. I have just found that the church encoding of the free functor is not stack safe unless you use a reduced encoding first. So you first reduce the encoding using the functor laws, and then you church encode the results, and that can be made stack safe. Most likely it's similar with monads, because the tree encoding has twice the recursive use of the type, so that could probably going to prevent you from being stack safe. This is difficult enough to make stack safe, but maybe possible. Certainly, I would, if I were to make a library, I would use reduced encoding and church encode that as an option, but also provide non-church encoded reduced encoding of the free monad as an option. There's almost never any advantages in using a non-reduced encoding. But there might be an advantage in using church encoding. So again, let us consider what happens if you do a free monad over a functor. So you can actually save yourself a lot of trouble, because if f is a functor, then we can use the identity, which says that this expression is equal to f of this, which is this. So now we get a recursive definition, which is much simpler, which is a free monad over a functor. So I would also provide this as an option in the library, because it's a much simpler and more efficient, perhaps, definition. And also it shows you that a free monad is different from the monad itself if you just substitute it into here or into here. So the free monad over a monad is not equivalent to that monad. So don't do it. As an exercise, we can ask what is a free monad over a pointed functor. So again, all we need to do is we need to start with a tree encoding and try to reduce it. So how do we reduce it? Well, first we start with this. Clearly the pointed functor doesn't need this part of the disjunction. And clearly we can start with this encoding, collapsing all those flat map functions into one. And the result is going to be this. And that's it. We cannot really simplify this because we don't have a pure encoded. So we cannot say, oh, let's only have this case, because we cannot encode a FA. So we don't have a pure method for free. We have a pure method for FA itself, but not for free. We have eliminated that. So we cannot encode a FA here. We cannot save us this part of the disjunction. Therefore, this is the reduced encoding. We use again the identity for the existential type to get f of this. So therefore, the reduced encoding is fa plus f of this. So it's still going to be recursive. Free m of f is fa plus this. So that's the reduced encoding. Here's the code for the free monad. So I'm not going to spend a lot of time on this. Let's consider the free applicative, which is an interesting type class. It has two methods. We choose pure and app because the other choice would be, for example, wrapped unit and zip. They do not return the type that we're constraining. So wrapped unit returns f of 1, not f of a, and zip returns f of pair AB. But we cannot have that as a return type. The return type must be the simple FA with no changes. If it is not that, then our type class is not inductive. So if the type class allows us to have a formulation equivalent to the previous formulation of the type class, such that the new formulation contains only methods of inductive type signatures, that is, methods that return the type class being constrained, then it's an inductive type class. So as before, we think about which methods to choose, and we choose pure and app because map can be recovered from these. So the tree encoding is straightforward, and note we again have two usages of the recursive type. Let's derive the reduced encoding. That's going to be this. So how do we derive that? So we reason about what structure of the values we will have. Either we take FA and we apply a bunch of apps to it, or we take A and apply a bunch of apps to it. So we can encode, if we have an A to which we apply an app, we can encode that as something like this. So we can do an app with a pure here with a different type signature, because that's basically going to be a map due to the laws of the zip. So it's going to be equivalent to a free app on the left, just the one that is on the right, we put it on the left, and on the right we put some other thing. So that means the first one does not have to be a pure value. The first value in this product, it does not have to be a pure value. It can always be a wrapped f. But then we cannot encode the pure value, so we still need that case. So therefore we need only two cases, the pure value and a wrapped constructor with a free app. So that's therefore the reduced encoding. A free applicative over a functor is taken from here. We use this representation. And what we find is that we cannot really reduce this using the identity for the existential type. Because this is not of the form exists z and then fz and z goes to something. It is not z goes to something. It is a type constructor. So therefore, free applicative over a functor, it looks like this. We can still reduce this, but we do need to have a wrapped constructor, but the A is outside of the recursion. So the only gain that we have is that if the type constructor f is already a functor, then the pure value is outside the recursion. Other than that, it's a very similar construction. So first we construct a recursive case, which can be seen as a reduced encoding of free zippable. That is a type class where only the app method is given and no pure. So this is a free zippable. And then we do a free pointed out of that. So it's a free pointed over a free zippable over a functor f. And we see that, again, free applicative over applicative is not the same as that functor. So Here's the code of the free applicative in the tree encoding and in the reduced encoding. So, having gone through all these examples, let us generalize. What are laws of the free type class constructions? So we will consider a general inductive type class, and for simplicity we will not consider type constructors here, only ordinary types. So the type class will have methods of this type signature. But you see, all the examples we have seen have been inductive. So it's going to be equivalent for them, except it's going to be much more syntax for all these type constructors and type parameters. So I'm not going to go through laws for type constructor type classes, because they're going to be analogous up to a much more complicated syntax. I'm going to consider in inductive type classes that have just ordinary types as elements of or instances of type class. So a type class with a method functor C has these methods, and this is the definition of a free instance of C over a fixed type Z. So that's we have seen. So there are several general properties that this construction has. I'm not going to consider church encoding because church encoding is equivalent to this. It has exactly the same properties, but it's much more complicated to reason about. It's just a much more complicated type. I'm going to use a recursive algebraic or polynomial definition of a free type instance. The first property is that this type is actually an instance of type class C. So, in other words, we can implement these methods. All the methods are summarized in a single value of this type, and so once we show that we can implement a value of this type, we're done. We have implemented the methods. Another property is that it is a functor in Z, so it has an F map, which works by changing the generating type. Another property is that if we have a specific type of that type class C, we can implement these functions run and wrap. So the wrap will lift a value of Z into the free type class instance, and the run will take a free type class instance. It will also take this extractor function, which translates Z into P, and then it can translate the entire free instance into P. These functions have certain laws. So the first law is that run over wrap is identity. So what does it mean? If you wrap a value Z and then you run it, then it's the same as if you did not wrap. So you transform Z to the same P if you first just take Z to P, or if you first wrap it and then you run it, you get the same P. So that's this law. The second law is the naturality of run. So the run has this Z type argument, and in this type argument it is natural. So the naturality law, as usual, it is a law of how to put F map outside or inside of your function. So this is typically an equation of this sort. You have an F map, either the right-hand side has no F map or it has an F map on the other side. So in this case it has no F map. Here's a type diagram. So you start with a free instance of C, over y. You can transform it into a free c over z using the fmap function, fmap of f, where f is an arbitrary transformation y to z. And then you can run this into p, or you can run this into p, and that shouldn't be different. So you can first run directly with the combined function, or you can run first by transforming into z, and then you can run from z, and it should be exactly the same. So that's what this law specifies. Another important property is the so-called universal property. And this property says that the runner is universal. You only have one runner. So if you have, for example, to run into two different types, then the same runner works for them in a way that is compatible. So suppose you have two types P and Q, and you want to run into P and run into Q, and there is a function that transforms from P to Q, and this function preserves the type class. So it's not just an arbitrary transformation from P to Q, it's a transformation that preserves the type class. The property of preserving the type class is this diagram, which is that here is the methods functor of the type class, and here's the methods for P, and here are the methods for Q. And if you map P to Q, then the methods are also mapped to each other. So in other words, for instance, if the class is a monoid, then the function f must transform the unit element of the monoid P into the unit element of the monoid Q, and it must transform product in the P monoid into the product in the Q monoid. So that's automatically guaranteed by this diagram, because the ops value is already all the methods put together into a single value. So if the function f from P to Q satisfies this commutativity condition, then what I say it preserves the type class. And for these functions f, you can see this diagram that you can run first into P, and then you transform into Q, or you directly transform into Q, and that's the same function run that does it. So that is another kind of property that is quite important. So let's see how these properties can be proved. So first, I will repeat the code for the universal construction of a tree-encoded type class. Now, notice I have been using the tree encoding here. Again, this is the simplest encoding. It is mechanically produced, does not require any reasoning in order to be implemented, whereas the reduced encoding requires some reasoning and proofs to show that it is actually reduced and adequate for encoding all possible values. And so it's much more difficult to reason about, although it can give you advantages in performance. So that's why I'm reasoning about the tree encoding here. So I implemented the function ops that basically says that the free type class has the methods that are required for the type class C. So the ops is a function from C of free to free. So that's this function, and that's the first law that I need. I implement this. The second is that I can wrap. That is trivial. I just put the wrap constructor. Then that I can interpret. The interpreter is just a general interpreter, which we have seen. I show that it is a functor. Well, this is a simple exercise in making a functor instance for a recursive type, where I use recursively the map function in the ops, because ops is a recursive part of the type. So the first law is that if we run on wrap, that's an identity. Now both sides of the first law are functions of this type. So therefore we need to apply both functions on arbitrary value of this type. So let's call this value free_cz. And also, instead of this, because we're working in this type, the runner needs an argument of this ops type. So we need to have the ops for the free type constructor. So that's our ops defined above. So if we do that, and we substitute the code, then this is what we get. Now, if we look at this function must be identity, which means that it's a free_cz match something, and this match should be just identity cases like this. And indeed, they are identity. The wrap case is just wrap, which is defined like this. That's a definition of ops and wrap. So ops requires us to execute a recursive call to the run. And so we can use the induction assumption that run of wrap is identity. And that assumption can be applied to recursive calls of the function that we're proving the law for. So therefore, this is identity. So that's a map on identity. So that's just ops of CF, which is equal to that. So that is, again, identity. The second law is a little more involved. It's a naturality. Now, I could say, well, naturality is obvious because our code doesn't look at the type, but we can prove this formally. So again, we look at the two sides of this equation. They're functions of this type, and so we apply both sides to an arbitrary value of that type. And then we just substitute and compute the left-hand side, which is going to be this. And the run of that is going to be that. And then we compute the right-hand side. So we already see that the wrap case is the same. And what remains is to demonstrate that the ops case is the same. Now there is a slight difference between these two expressions. And the difference can be resolved because we can use the induction assumption for this. So we are proving the law of this kind, and we can use this law for the recursive call here. And so if we do that, we can assume that this is true, and then that's exactly what remains to be demonstrated, because we can do the map. So this is a functor whose map method we're using, so we can use the composition law for the functor. And that's exactly the expression that we have here that remained not equal. That's a composition of two maps. So if we simplify that, we get this. So the universal property is slightly more involved yet, but it is proved in a similar way. So both sides are functions of this type. So we apply both sides to an arbitrary value of type free_cz. We'll compute the left-hand side, we compute the right-hand side, and we use the type class preserving property, which is this equation. or equivalently written as Scala code as this equation. So when we have f of ops p, we replace that with ops q of something. So ops p and ops q are assumed to be available. These are type class evidence for p and q. And simplifying the code, we put the code into identical shape. So that gives us the proof of the laws. Now, let's see what code I have here. That code is for the next slide. Another general thing we can do with a free type class is that we can combine different generating constructors. So far we have been only looking at a free instance of a type class C generated by a single type Z. But we can also consider several constructors at the same time, several generating types of constructors. And this would correspond in a monadic DSL that we have different sets of operations that are defined separately. We would like to combine them. And recall that monads do not compose in general. So it is in general not easy to compose different sets of operations. But it is actually easy in the free type class, because all you need to do is to take a disjunction, since the definition of the free type class is this. If you have several generating types, all you need to do is to have several parts of the disjunction here, Z1 plus Z2 plus Z3 and so on, which means that the free instance of C over several constructor is the same as the free instance of C over the disjunction of these constructors. So it is sufficient to take the disjunction and generate the free type class using the disjunction. Now the only inconvenience is that you would need to inject parts into the disjunction, and that can become cumbersome. I will show code in a minute. And the church encoding actually makes it easier to manage this situation. So the reason is that the church encoding for an inductive type class, it looks like this. If you have several constructors, then it will be like this. You can take the disjunction and transform it into this sort of expression. Now you can do the trick of type classes, so you can encode each of these as extractor type class. And then the church encoding would look like this. And you can even simplify it further by saying that even this is a type class constraint on X, which means that X must be of type C. And so the church encoding would look like this. So in this form, it is an easier code to maintain. At the same time, we find that this definition actually works for any number of generators and for any type class C. It's a general formula for a church encoded free instance of type class C generated by any number of given types. So in this very concise form, it's very easy to implement as well. Let's see how that works. In order to test this, I have three type constructors that are not functors, in other words, unfunctors. And they describe different kinds of operations in some kind of imaginary business logic. The first unfunctor adds a name to a database, and returns a database ID and gets name by ID. The second unfunctor logs a message, returns unit. The third unfunctor creates a new ID. So these are just, for example, and I define generic transformations from each of these unfunctors to the option functor. And these are just defined in arbitrary ways for testing purposes only. This is not useful for any kind of application. This kind of transformation, I return none a lot. This is just testing. I'm testing that all the types fit together. So the first way of combining the three operation constructors, I'm going to put them into a free functor. And as we have seen, all I need to do is I need to take a disjunction of all these type constructors. So let me define this unfunctor as a disjunction of the three type constructors. Now I also need to define a generic transformation from the new unfunctor to option. Let me put the syntax a little easier, like this. Now notice that I need to write this code. This code is pure boilerplate, but it depends on how I defined my unfunctor here. If I add another one, then this entire code would have to be revised, and this is a bit of a burden. Now, defining a free functor in the reduced encoding, this is straightforward. In order to use it, I need to lift values from each of the unfunctor into the free functor. So I define these lifting functions, and again I have boilerplate that depends on how the order of disjunctions is chosen. Now this is an example computation where I require this type annotation in order to lift. I could have called these functions directly. Actually, let me call them lowercase. I could have called them directly, or I can do this, but I have to do it. So let's see how the same works in the church encoding. So first I define extractor type classes, and then I define the church encoding. This is the entire church encoding. It has a type parameter G, and then there are 3 type constraints for each of the unfunctor extractors, and then a functor type constraint, and I'm done. This is the entire encoding. The functor instance is trivial, but it is not stack safe, unfortunately, because we know that the church encoding of the tree encoding of a free functor is not stack safe. Now, the boilerplate for lifting does not depend on the order of the unfunctors. There's no notion of order anywhere. If I need a 4th one, I can just add it here, 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 and here, and that'll be done. There's no possibility of making a mistake there. And finally, I run the computation. The extractors I need to declare, and I'm done. See, the run is very simple. I don't need an extra runner. I have less code than here in the tree encoding. Another important thing that we can do is combining different free type classes. So suppose you have 2 different type classes, C1 and C2, and you want to combine them. There are several ways of doing that, and one is to use functor composition. So for example, I can do free C1 of a free C2 of Z. I could do that. There are disadvantages in doing this. one big disadvantage is that the order of composition actually matters in terms of what semantics I get. If these type classes return effects, then the effects are combined and nested in this order and not in the opposite order. So I would not be able to encode this order of nesting. I must encode always this order of nesting. And of course, all the operations that I want to execute in C2 need to be lifted through the functor C1. I can do it because it's a functor, as we have seen. And this only works for inductive type classes, of course. Well, that is not a big limitation, perhaps, since most of our type classes are inductive. Not all. For example, traversable is not inductive, so there is no free traversable that can be encoded in this way. But these are significant disadvantages. Most importantly, we are not free to encode arbitrary nesting of effects. The second option is to use the disjunction of method functors, and then you build the free type class instance using this C. In other words, you make a new type class that has all the methods of the previous type classes. Disjunction of method functors is equivalent to conjunction of the type class evidence values, because type class evidence values are of type function cx to x. And so this disjunction is equivalent to taking a conjunction of those functions. So that's the same as building one big type class with all the methods put together. Now, this is of course not ideal, because you would have to change the code if you wanted to combine different type classes. But church encoding can give you this combination for free, because all you need to do is to write this kind of type, and then obviously this is just the product of C1, C2, so you have this formula where you can put different type classes here and different generators here. And so the church encoding automatically gives you a way of having a free type class instance for any combination of type classes and any combination of generators. It's a very powerful mechanism. Let's consider just two examples. One is for curiosity. What if we combine the functor and the contrafunctor? We would have a type class that is at once a functor and a contrafunctor. And that's possible. We can do it. The question is, what do you do with this class? Because this class is going to be free encoding. So you need to interpret it into some specific type class. So you could probably interpret it into a profunctor. Although I don't know what is the use case for this. And a better example is to combine monad and applicative. Now this is actually useful in practice, because monad and applicative encode slightly different kinds of effects. Monad encodes sequential effects. Applicative encodes effects that are partially parallel, so they're not necessarily completely independent, but the effect part can be run in parallel. So computation with applicative functor can be parallelized very easily, but computations with monads cannot be parallelized because they are sequential. The next step depends on the value of the previous step. And the effect also depends on the value of the previous step. So you cannot start running the effect before you know the value, but with applicative you can. Now, ordinarily, a monad also has an applicative instance. However, in some monads, in other words, you can implement zip if you have flat map, but in some monads, there is a non-standard implementation of zip that has specific advantages. In other words, an implementation of zip that is not equal to that which you get out of a flat map. And you do that for specific reasons, either for performance, so it could give you the same results, but it will run effects differently and it would have different performance. For example, imagine that you have a future monad, and then zip can be implemented as parallel execution of futures, and flat map is implemented as sequential execution of futures. So if you combined a monad and applicative in a free type class and interpreted that type class into a future such that the monadic methods, the flat map, are converted into flat map in the future, but the applicative methods are converted into parallel execution of futures using a special code. Then you get an advantage because each zip will create parallel branches and each flat map sequential branches. So let's see how that works in some example code. So here's the encoding of a free monad and applicative at the same time. So I put them into one type class for simplicity. I could have done it differently. I could have done it using the church encoding the way I described before. But this is more interesting because you can now see how you would run a combined free monad applicative over a type constructor G that has both applicative and monad instances. The way you would do that is that, well, you would translate, of course, wrap into wrap, pure into pure. Flat map, you would translate like this. You would run, and then you run this, and you run the flat map in the target monad, but the applicative method you translate like this. You run in parallel, and then you combine them using the applicative method in the monad. So you see this run is not in parallel because this is inside the function, which is this function, which will be called only inside the flat map after the first effect is finished. But these two effects are going to be run in parallel. So if I implement the interpreter like this, then I will automatically translate all the applicative operations into parallel executions, potentially parallel executions. Let's see, for example, for future. I just translate the same into futures, and this is actually going to be a parallel execution of futures because we know what Scala does. And once you have a future, it already is scheduled and run. I give it an execution context, and it's already running. So in this way, I can have, so I implement the type class instances for functor, monad, for it's more or less boilerplate. I just do a little bit of simplification. It's not important. So let me just skip this. And then here's my DSL. I have some operations. I make a free monad out of it, which is at the same time a free applicative. And then I run it through the future. So I can run my code monadically. So this is monadic code. The lift is just a method that I defined to make it quicker to lift things. It's a wrapper. So basically I generate an ID, then I generate 3 new IDs, then I validate them in parallel, and I wait until all of this validation is done, and I close the session. So this is a combination of monadic and applicative methods at the same time. And the interpreter is just some translating these into specific business logic that I imagined. And this is all more or less boilerplate. So basically, when I run this computation is, of course, just a pure value, it doesn't do anything. It's a pure data structure that describes what needs to be done. But when I run this computation, and automatically all these, the zipped parts, become executed in parallel, but all the monadic parts are executed sequentially. And I don't need to worry about the order of these things. I can nest them in any way I want. For example, I could define first a validate using monadic, then I combine different validates using applicative, and I again put the results into a monadic context. It's fine, it's all working. Right? It all works in arbitrary order. This is what I was indicating here, and this is an advantage over this method, the functor composition, where I would have to choose whether I have monad outside, applicative inside, or monad inside, applicative outside, and whatever I choose, I can only then encode one of those combinations. So this concludes this chapter, and here are some exercises for making tree encoding, reduced encoding, working with inductive type classes, implementing DSLs, implementing the church encoding, simplifying quantified types, and deriving a reduced encoding out of a tree encoding for different cases. This concludes chapter 10.